In this video, we're going to cover 27 practice questions that cover the entire grade 11 functions math course in just over 2 hours. So whether you're reviewing for the exam or any unit test, or you want an introduction to what the course covers, this will be a thorough overview of the entire course. The topics we're going to cover include the following: functions and transformations, rational functions, quadratics, exponential functions, trigonometry, sinusoidal functions, sequences and series, and annuities and compound interest. Unit 1 is all about intro to functions. Unit 1 is functions and transformations. The first question says, graph the four relations shown, list the domain and range of each, and identify which is a function and why. So the first one is y equals the absolute value of x. So what that means is that whatever you put in for x, y is just the magnitude of that, or the positive value of that. So if you put in a negative value, it becomes positive. So if we graph those on a grid, as shown here, we just have a line that's going up to the right, and then on the left side, it's going up to the left. And so this is a function because every x value corresponds with only one y value. Another way to say that is that every x value has only one y value that comes as a result of it. And so this is a function, so we can use function notation. We can write that as f of x equals the absolute value of x. It also passes the vertical line test. That means the vertical line never intersects the line more than once. So we can now write the domain and range. The domain is x is the set of all real numbers, and there's no restrictions on that. It's going to keep going out to the right forever. It's going to keep going to the left forever. The range is y is a set of all real numbers, but you can see that it never becomes negative. So that means that y is greater than or equal to 0. So there's your domain and range of that first function. The next function that we investigate in this course is the function y equals 1 over x. And so if I put negative 2 in, 1 over negative 2 is negative a half. Negative 1 in, 1 over negative 1 is negative 1. 1 over negative a half is actually negative 2. If it's 1 over 0, that's not allowed in math, so that becomes undefined. If we continue that with the positive values, we get the values shown, and they're just the same as what we had with the negative, except they're now positive. So now what we do is we label the axes. I'm going up here by every square is a half, and then I'm putting those points on the graph like shown, and I'm drawing a smooth curve through those points. Now, you'll notice that when we approach 0, on one side it goes down to negative infinity, and the other side it goes up to positive infinity. And so right at that line x equals 0, that actually is going to be a vertical asymptote, and the y equals 0 is a horizontal asymptote. You can see those labeled with the dotted lines. And so that is a function because it passes the vertical line test, and every x value corresponds to only one y value. So we can label that with function notation f of x equals 1 over x. All right, so domain and range. Domain. X is a set of all real numbers. It goes on and on forever on the right, forever on the left. However, right at 0, it was not allowed. So that asymptote is actually going to be our restriction. And the same thing with the range. The y value cannot be 0, and that asymptote is the restriction. Otherwise, all y values are allowed. So now we go ahead and we look at a third parent function, and that would be y equals the square root of x. And so I'm choosing x values that are perfect squares because when I take the square root of them, I want whole numbers. And so 0, 1, 4, 9, 16 gives me 0, 1, 2, 3, and 4. Now, not all these are going to fit on the graph with the grid I have and with the number of squares I have, but I am going to fit at least 3 of these on. I have 0, 0, 1, 1, and 4, 2. When I draw a curve through those points, it looks like that. And that is a function because it passes the vertical line test and because every x value corresponds to only one y value. Now you'll notice if I put negative 1 in, the square root of negative 1 is not possible in terms of the real numbers. And so that is not something that's allowed, which is going to restrict our domain and range here. So any negative values under the square root are not allowed. So that means the domain is x is a set of all real numbers such that x is greater than or equal to 0. And the range has the same restriction. Y is a set of all real numbers such that y is greater than or equal to 0. It touches that point 0 but never goes below it. So now we go ahead and look at the next function, x equals y squared. It's going to look remarkably similar to what we have on the left, but with one distinct difference. Because the y values are squared, I'm going to give the y values first and then square them to determine what the x values are. And so as we do that, you get Negative 2 squared is 4, negative 1 squared is 1, 0, 0, etc. And so we go to label those points on the graph, and what we actually get is we have something, as I already mentioned, that looks remarkably similar to what we had on the left, except it's not just that curve on the top, it's also the curve on the bottom. It's a complete sideways parabola. This is clearly a non-function, and that's because there are several x values that actually have two corresponding y values. In fact, every x value to the right of 0 is going to have two corresponding y values, and so that's not a function. It also fails the vertical line test. If we draw any vertical line to the right of 0, it's going to go through the function twice. So you might be wondering, why is this different than what's on the left? Like if I take the square root of both sides of the example in D, does it not become what is C? Well, it actually becomes plus or minus the square root of x. And you'll notice on the left in example C, that was just the positive square root of x. In other words, that when I take x equals y squared, that actually gives me the top and the bottom of the sideways parabola, not just the top of it. And so that's going to make it a non-function. So the domain is x is a set of all real numbers, and you can see that x has to be greater than or equal to 0. And the range has no restrictions. It's going to go up forever and down forever as well. All right, so there we go. Those are the examples. If you want to see y equals x squared, that's coming in a later video on Unit 3 on Quadratics. And so you can see how that's being graphed if you want to see that as well. That is very foundational to this course. Example 2. The graph of a general function f of x can be transformed to create the graph of the function g of x equals negative 3 f. That's a function of negative 2 x minus 1 minus 4. Describe the transformations that would be applied to g of x. Well, what we need to do first is we need to identify what the a, k, d, and c values are. And so the a value is negative 3, the k value is negative 2, the d value is 1, because the general form is x minus d, and the c value is negative 4. So now what we're going to do is we're going to list how those restrictions apply. Remember, in general, it's a times f of k, x minus d, plus c. And so the a value being negative 3 is going to mean that it is a vertical stretch by a factor of 3. Vertical stretch by a factor of 3. Now the negative also has something to affect that, and that negative is going to flip it over the x-axis. Notice that's a vertical flip. So the x is the horizontal axis, so it's going to reflect or flip over that horizontal axis. It's going to vertically flip. It's very important you keep that clear from what's happening with the k value. So k value being negative 2 means it is going to be a horizontal. Now, it's 1 over 2 is the stretch or compression factor. So this is a compression. 1 over 2 is going to be a half. So it's a horizontal compression with a factor of 1/2. Factor of 1/2. The negative is going to flip it or reflect it over the y-axis. That's going to be a horizontal flip, horizontal reflection, which happens over the vertical axis. All right, so now we move on to d. d is equal to 1, and that means it's going to shift 1 unit to the right. d is always a shift left to right. And the c value, which is the very last value, is going to shift it 4 down. That's always going to be a shift up or down. In this case, being negative, it's shifting 4 down. And so now that we have those transformations, we're going to now graph that on the graph shown. I've set a scale, so every square is 1, just to make it nice and easy to see. So graphing f of x equals 1 over x, just like I did earlier in this video, you can see those key points. We have 6 key points, and then we go ahead and we graph our curve through those. I'm just drawing that first function as a dotted line just so it doesn't get too messy with everything else. There's going to be a lot of functions on here. It's going to be a little cluttered, but that is f of x equals 1 over x. Now we're going to graph it just with the a value, the negative 3 applied. So I'm going to take the value 1, 1. That's the easiest one to start with. I'm going to multiply the y value by 3. So it's going to go up to 3, and then flip it over the x-axis down to negative 3. So there we go. That point transforms down to negative 3. And then when I look at the next point over, which is going to be at 1/2, that becomes 3 over 2, or 1.5, and then flips over the x-axis down to negative 1.5. The point at 1/2 and 2 then goes up to 6, and then flips all the way down to negative 6. And so I do the same thing with all the points on the left. I multiply essentially the y values all by negative 3, and I get the points shown. And so then I draw the curve through those clear points, and making sure those points are nice and clear even after I draw the curve so I can transform those in the future. That labels as y equals -3 over x. The a value has been applied to the function 1 over x. So now I'm going to go ahead and apply the k value. For the k value, I'm going to multiply each of the x values now by a half and then flip it over the y-axis. So 2, or -2, becomes -1, and then it flips over the y-axis to become +1 at the same y values now. Same y values. And so -1 becomes -1/2, flips over to become 1/2. And then a half, or -1/2, becomes -1/4, flips over to become 1/4. And then I can draw my curve through those 3 points as shown. I'm going to do the same thing with the bottom right curve. I'm going to multiply each of those x values effectively by -1/2. It's going to flip it over the y-axis, and it's going to make them become half the distance to the y-axis that they were previously. Now I draw my curve through those key points, and I have it looking something like that. And that is now with the -3 and the -2. So y equals -3 over -2x. And so the last thing we want to do with our transformations is we want to graph the shift right and the shift down in this case. And the easy way to do this actually is to start by recognizing how the asymptotes will shift. Because it's shifting right 1, that means the asymptote that was at x equals 0 is going to become x equals 1. And the asymptote that it was at y equals 0 is going to become y equals -4. And then it's going to have the same shape. In other words, it's going to be the same distance from the two asymptotes and where those join compared to where they were from the origin previously. So if it was over 1 and up 1.5, we're going where those two asymptotes join, over 1 and up 1.5. And there's one of the points there. We're going to continue that pattern with all the other points. There's another point there. I went over 1/2 and up 3. So I'm going to go over 1/2 and up 3. There's another key point. And then that last key point way up at 1/4 and 6 is going to be a 1/4 from where the asymptotes join and 6 above it. And so we join those 3 points up like so, and that's the right side of this. I do the same thing with the red dots down in the bottom left. I'm transforming each of those right 1 and down 4. You could literally move them from where they are over 1 and down 4, or you can compare where they are compared to where those two asymptotes join, as I already described. And so what you're going to get is you're going to get two of those points that are actually going to show. The third point isn't going to fit on the graph that I have, but it's going to look something like that. And so what we have in blue is our final function g of x. That is g of x. And so g of x, or in this case, I could just write it as y equals as well, but it's equal to -3 over -2 x minus 1 minus 4. So I'm just going to write that out here as well on the left so you can see what that looks like applied to this specific parent function. What was listed at the beginning of this question was those same transformations that could be literally applied in the same way to any parent function that we've gone over previously. I chose the reciprocal function just because it's a little trickier for students to grasp, and it's a good example to look at. So our domain and range, the only restrictions we have on those are the asymptotes. So x cannot be 1 and y cannot be -4. And the equations of the asymptotes are, we already showed those as we graphed those earlier, what's shown right there. So we fully transformed a reciprocal function. We've looked at the parent functions and what each of those are. And we've got a really good summary of what Unit 1 is, all about functions and transformations. Unit 2 is all about rational functions. We're going to multiply and divide and add and subtract these rational functions shown on the screen in front of you. Unit 2 is all about rational functions, but it's important we first look at a couple of examples to remind ourselves of some key properties of how to factor different things. So the first example, we have 4 terms, and we always try to do 4 terms by factoring by grouping. I go ahead and I common factor to the first 2 terms, and I take an n squared out. I'm left with n plus 3. And then I can look at the next 2 terms, and I can take a -9 out. And again, I'm left with n plus 3. If we've got an n plus 3 in both those terms, that's what we want. And so we can write that as n squared minus 9 times n plus 3. That's called the difference of squares. Now remember, a difference of squares is in the form a squared minus b squared. And if we have that, then we factor it by going a plus b times a minus b. And so what that means here is that n squared minus 3 squared is what we ultimately have. Gives me n plus 3 times n minus 3. times the n plus 3 that I already had written above. And so now that is fully factored, but we could just combine the n plus 3 terms to get n plus 3 squared times n minus 3. And now that is fully factored. So always watch for that. You never know when a difference of squares or something could pop up after you've already factored the first step. Now for example B, what you'll notice, if you try to do the same thing, we go ahead and we take an x out of the first two terms, but we can't common factor anything out of the next two terms. And so that's a problem. So what we need to do is we need to look at a different strategy. So in this case, what we can do is we can actually look at the three terms and see if we can make that a perfect square. Now remember what a perfect square is. A perfect square is something that is in the form of a squared plus 2ab plus b squared. And if that's the case, then we can write that out as a plus b all squared. And so what we're going to do is we're going to see if we can write that out. If there's a minus before the second term, it's a minus between the a and the b. Now here it's just a plus, so we're good with the positive. So we're going to write that as a squared plus 2 times a is x, and b is 4, plus 4 squared. That's exactly right. So then we can write that as x plus 4 all squared minus 25y squared. Now what we have is we have one term squared minus another term squared. That is a difference of squares. Now to see this a little bit more clearly, I'm just going to write the 25y squared as 5y all squared, keeping the x plus 4 squared the same. And so that 5 squared becomes the 25. And so now you can see the a squared minus b squared. So the a term is x plus 4, the b term is 5y. So we're going to add it, and then we're going to subtract the 5y from the x plus 4. Now the final thing we want to do here is we want to go ahead and we just want to put x then y then the non-variable term. And so x plus 5y plus 4 and x minus 5y plus 4. The order can be changed, no problem, provided the signs stay the same in front of the terms. So there you go. We factored two examples. We're going to see lots more factoring in the questions that are to come. So one case we saw in rational expressions was when we multiply or divide two things. And so what we have to do is we have to start by factoring each of the numerators and denominators of each of those fractions. And so we go ahead, 4 minus x we don't need to factor, but the 5x minus 20 we can common factor, which becomes 5 times x minus 4. The 2x squared minus 5x minus 3, this is sometimes called a tricky trinomial. We have to factor this by finding two numbers that add to the middle term of negative 5 and that multiply to the first term times the last term. 2 times negative 3 is negative 6. So we start listing factors of negative 6. 1 and negative 6 work. And so we go ahead and we decompose the negative 5x into those two terms with the x associated with those as well. So the negative 5x becomes 1x minus 6x. And now we factor by grouping. We go ahead and we common factor out of the first two terms an x, we're left with 2x plus 1. And then we common factor a negative 3 out of the next two terms and we're left with 2x plus 1 again. Because those two things in brackets are the same, we've done it properly and we get x minus 3 times 2x plus 1. Now we go ahead and we do the same thing with 6x squared minus 17x minus 10. In this case, we're trying to find two numbers that add to negative 17, the middle term, and multiply to the first term times the last term. 6 times negative 10 is negative 60. In this case, we go ahead and we could start listing factors of negative 60. We could, if you see it right away, you could write those down. But just so you can see here, 1 and negative 60 would add to negative 59. That won't work. 2 and negative 30 would add to negative 28. That wouldn't work. But 3 and negative 20 adds to negative 17. That does work. And we knew the bigger number had to be negative because it added to a negative. So now we decompose a negative 17x into two terms, which gives me 3x and negative 20x. And then we go ahead and we factor by grouping again. We can take a 3x out of the first two terms. We're left with 2x plus 1. And then we can go ahead and we take a minus 10 out of the next two terms. And that gives me a 2x plus 1 again. The negative 10 divided by negative 10 makes it positive 1 at the end. So this gives me 3x minus 10 times 2x plus 1. And now we have factored all the terms and we can start putting it together on the left side there. So go ahead and 4 minus x. That's being divided by the 2x squared minus 5x minus 3 became x minus 3 times 2x plus 1. And then we're dividing that by what's on the right there. Now, remember that division of a fraction is the same as multiplying by the reciprocal. So let's go ahead and just take the reciprocal right now. I'm going to do this in two steps, so not to confuse anyone here. But I'm going to first take the reciprocal, and then I'm going to show the factored forms of everything in a moment for this second fraction. So 5x over minus 20 over the 6x squared minus 17x minus 10. We flip the numerator and denominator and we get that. Now I'm going to go ahead and write that out factored. The 6x squared expression was 3x minus 10 times 2x plus 1, and the 5x minus 20 became 5 times x minus 4. Now I can go ahead and recognize that x minus 4 and the 4 minus x are very, very similar. In fact, they look like they might cancel out. Notice that if I common factor a negative out of this, I get negative 4 plus x. And so I could rewrite that as negative, and then we get a x minus 4. And so if I have that, what I can do is I can go ahead and write this out like so, negative x minus 4, and then over x plus 3, or x minus 3 rather, times 2x plus 1. And then we're going to multiply that by everything. And so really that means that everything in the numerator gets multiplied together, everything in the denominator gets multiplied together, and we can cancel everything out that is the same in the numerator and in the denominator. And so we just have the 5 and the x minus 4 there in the denominator. And let's start canceling things out. So the x minus 4 in the numerator cancels out with the x minus 4 in the denominator, as does the 2x plus 1. Those both cancel out and simplify some things for us here. And so what we're left with is we're left with negative 3x minus 10, and we divide all of that by 5 times x minus 3. So the 5 is going to be written at the beginning just to make it a little cleaner. And so now I can go ahead and expand this out just to get rid of the brackets here. I get negative 3x plus 10 over 5x minus 15. And that would be our final answer, except we also want restrictions. Because we've canceled things out, we need to make sure that those have been accounted for in my answer, because they don't look like they're there anymore. And if you didn't have the restrictions, nobody would know that they were there originally. Those restrictions that cancel out are actually holes. They form holes in the graph, whereas the restriction that stays in the denominator after everything cancels, that forms a vertical asymptote. And so notice that those two things occur. We actually have 3 restrictions in this case. And so I'm solving the restrictions there over at the far right side. The 2x plus 1 restriction that was a hole, when I rearrange that, I get x equals, or cannot equal, negative 1/2. And then I have the other restriction of x minus 4. That is also going to be rearranged to give me x cannot be 4. And then the last restriction, the 5x minus 15, is the same as what was above, which was x minus 3. That's just an easier way to find that. It's the same restriction. So we get x cannot be 3. So those are our 3 restrictions. The last one, the 3, is an asymptote, and then the other 2 cause holes to form. And so there you go. We have stated the restrictions, and we've simplified that as shown. Lots of good factoring there and good simplification that needs to be done. Now we run into a situation where we have to subtract one fraction from another, or one rational expression from another. And so just like we did before, we have to start by factoring. And so we go ahead and we say, okay, well, that negative 1 is what 2 numbers have to add to, and they have to multiply to negative 6. We know that the bigger number has to be negative in order to add to a negative. And so the factors that work are 2 and negative 3. Because this is a simple trinomial, we can go ahead and factor this directly. We don't need to decompose it, but if you wanted to, like we did before, it would still work out. But the nice thing about simple trinomials is you can literally just write the positive 2 and the negative 3, and that's your final answer. Now the next one is actually a perfect square. And one way we can check that to see if it's a perfect square is we see the square root of the first term is k, the square root of the last term is 2, and is the middle term 2 times k times 2? And if it is, it's a perfect square. 2 times k times 2 gives us 4k. So that means that k squared plus 2k times 2 plus 2 all squared is another way to look at that, is k plus 2 all squared. Okay, so that's a perfect square. You could factor that just like we did for the k squared minus k minus 6. That would work out the same way. But if you recognize something's a perfect square, you should go ahead and factor it that way. So we go ahead and we write this out as 5k over k plus 2 times k minus 3, and then minus 4 over k plus 2 all squared. Now the goal here is to get a common denominator. You'll notice that they both already have a k plus 2 in them, so the only thing we have to do to the fraction on the left is we have to add another k plus 2. In order to add it to the denominator, we also have to add it to the numerator so that nothing changes in that fraction. So we're going to multiply the top and the bottom by k plus 2. That is the lowest common denominator. Now what we're going to do is we're going to do the same thing for the other fraction. It already had 2k plus 2's, so we're going to multiply that by k minus 3 on the top and the bottom. So k minus 3 over k minus 3, that keeps the fraction the same. That's effectively multiplying by like 1 over 1, but it's going to show it nicer so that we can get a lowest common denominator. So it's the same one as we had on the left, and we can now write everything over the same lowest common denominator. So 5k times k plus 2, we're going to expand that out, minus 4 times k minus 3. We can write all together in the numerator now because they have a common denominator. And so we get k plus 2 squared times k minus 3. The order of multiplication doesn't matter in the denominator. So now I expand this out using the distributive property in the numerator. 5k squared plus 10k minus 4k plus 12. And I'm going to gather like terms in a moment, but I'm just going to write that denominator out one more time. And so what we end up getting is 5k squared plus 6k plus 12 all over k plus 2 all squared times k minus 3. Now you'll notice here that there are still restrictions like we had before. Nothing canceled out, so these would form asymptotes if we were to graph this, but those restrictions are k cannot be negative 2 and k cannot be 3. Unit 3 is all about quadratics. We're going to find the max or minimum in various forms. We're going to simplify radicals. We're going to solve situations using the quadratic formula. We're going to show and learn how to do inverse functions and the discriminants. The first of the 5 questions that we're going to look at for quadratics says, what are the coordinates of the maximum or minimum for each of the 2 functions shown? Now, it's important to note that this is already in vertex form in part A. So a times x minus h all squared plus k. The a value is 3, which means that it opens up because it's positive. And the h and k represent the coordinates of the vertex. So that means the vertex is at 3, negative 3. And so if I did a quick sketch of what that might look like, you don't need to do something fancy, but just a quick sketch. So 3 and negative 3, somewhere around there. Then what I'm going to do is I'm going to draw a parabola that opens up. And what you can see there is that therefore it must be a minimum. And so we can say therefore it's a minimum at 3, negative 3. That's the coordinates of the maximum or minimum, in this case, a minimum. Now the second situation is not in vertex form. It's in factored form. And so what we have to do here is we have to let the y value, or f of x, be 0. When we do that, that's what's going to determine our x-intercepts for us. And so we're going to then say, well, that means that 3x minus 2 must be 0, or 3x plus 4 must be 0 in order to multiply together to give us 0. So we go ahead and we solve for each one of those. So 3x equals 2. Then we divide both sides by 3 and we get x equals 2/3. And then 3x plus 4 equals 0. So 3x equals negative 4. We divide both sides by 3 and we get x equals negative 4/3. But don't fear fractions. They're going to work out usually. And so what we're going to do here is we're going to find the x value of the vertex, because that's always, due to symmetry, going to be the average of those two zeros, or those two x-intercepts. So we add them together, we divide by 2, and then what we get is we get negative 2/3 divided by 2. Well, just if you can't work that out in your head very well, think about it this way. You could write it like a division sign, and then what that means is we flip it and multiply. So negative 2/3 times a half, well, that becomes negative 1/3. So what we have to do now is we sub that back into our original equation, f of x, in order to determine what the y value of the vertex is going to be. So we go ahead and we sub in x is negative 1/3. We have everything else the same. And so what we're going to do now is we're going to multiply the 3 times negative 1/3 for the first and for the second. So 3 times negative 1/3 is negative 1 in both cases. And so we get negative 1 minus 2 and negative 1 plus 4 with a negative out front as well. So we get negative of negative 3 times positive 3. 2 negatives makes it positive, and we get positive 9. So that vertex is going to be at negative 1/3 and 9. Well, which way does it open? Well, we look at the a value. The a value is negative 1. We've pulled that a value out, it's been factored out in front. So because that a value is negative 1, that means it opens down. And so what we can do is we can then say that the negative 1/3 and 9 is a maximum, and there are the coordinates of the maximum in that particular case. Question 2 is all about radicals. And what you want to start by doing is just pause the video and see if you can write down all the perfect squares that we're going to be able to take out of the different numbers under the radical sign. So there you go. There are the perfect squares, 1, 4, 9, 16, 25, etc. And so what we want to do is we want to take out the greatest perfect square root of 125. Well, 125 is 25 times 5. And so the greatest perfect square I can take out of 20 is only 4. So 4 times 5 is 20. So now I can write the square root of 25 as 5, and I can write the square root of 4 as 2. Everything else is the same. And so now 3 times 5 is 15. So 15 root 5, and 2 times 2 is 4. So 4 root 5. And now because they're the same radicals, I can add the number in front of the radicals. So I get 19 root 5. If those were not the same radicals, I could not add the numbers in front. Part B now, instead of being adding, has multiplication. And so in this case, we're still going to use the same process, but we're going to be able to multiply everything out at the end. So the square root of 98 is 49 times 2. And the square root of 8 is 4 times 2. And so what I can do is I can go ahead and write this out as, well, the square root of 49 is 7. And so I still have the square root of 2. And the square root of 4 is 2. And I still have the square root of 2 there as well. But remember, I'm not adding them together this time. So 3 times 7 is 21 root 2 that I'm left with there. And 2 times 2 is 4, and I have the root 2. And so now I can multiply the root 2's together, and I can multiply the non-radicals together. So negative 21 times 4 gives me 84. And then the square root of 2 times itself gives me root 2 squared, which is 2. So now negative 84 times 2 gives me negative 168. The third situation is a perfect square. A perfect square. Remember, if we have something like a minus b all squared, that's not just a squared minus b squared. It's actually like, if you think about foiling that out, first outside, inside, last, it has two sets of brackets. It gives you a squared minus 2ab. You have that middle term of minus 2ab plus b squared. So let's apply that in this particular case. Square root of 2 is a, so we're going to square that. And then we have the middle term, which is 2 times the square root of 2 times the square root of 3. And then the last term squared, root 3 all squared. So the square root of 2 squared is just 2. And then we have minus 2 times the square root of 2 times the square root of 3. We can multiply those together to give us root 6. And then root 3 squared is 3. So now I can combine the 2 and the 3. That gives me 5. And I still have the minus 2 root 6. I can't combine those because they don't have the same radicals. Now, question number 3. This says find the exact zeros of f of x equals 3x squared minus 12x plus 6. Determine the vertex and y-intercept, and then graph it. So the first thing I want to do in order to determine the zeros is I want to let the y value be 0, or the f of x be 0. So I'm going to go ahead now, and I'm going to try to factor out as much as I can. Common factor, we always want to start with that because it simplifies our life. Now I get it down to this, and I try to go ahead and factor what's in the brackets. Try to find two numbers that add to negative 4 multiplied to 2. Not possible. So if it doesn't factor, what we have to do is we have to use the quadratic formula. And so I'm just dividing by 3 just so that we can clearly see the a, b, and c values. And so the quadratic formula is x equals negative b plus minus the square root of b squared minus 4ac all over 2a. So the a value is 1. That's the coefficient of the x squared. The b value is negative 4, the coefficient of the x. And the c value is 2. So now we go ahead and we sub these in. We always sub them in without the x, just the coefficients. Negative 4 plus or minus the square root of negative 4 squared minus 4 times 1 times 2. And that's all divided by 2 times 1. And so now I'm just going to simplify that. Negative 4 is positive 4 plus or minus the negative 4 squared was 16, and then we have minus 8. If we keep going and we simplify that a little further, we end up getting the square root of 8 under the radical sign. And we know from the last question we did that that's actually the square root of 4 times 2, and the square root of 4 is 2. So we can write that as 2 root 2. So x is equal to 4 plus or minus 2 root 2, all divided by 2. Now, in order to get it so it's not a fraction, I'm going to common factor a 2 out of the numerator here. So taking out a 2, we get 2 plus or minus 1 times root 2, which you don't need to write the 1 there. And now you can see that what happens is the 2 over 2 will cancel out. And so we just get what's in the brackets, which gives me 2 plus root 2 or 2 minus root 2. Now that is your exact zeros, but that's not helpful in order to graph it. So we're going to get some rounded answers here as well, 3.41 and 0.59, because that'll allow me to actually put that on the graph to see what's happening here. So the exact value is on the top and the approximate ones are below. So now what we want to do is we want to determine the vertex. And the x value of the vertex, if something is already in standard form, is just negative b over 2a. Because what we're doing is we're adding and subtracting a value from that. And it's pretty clear here. We're just adding root 2 and subtracting root 2 from that. So negative b over 2a, I'll put this in to convince you that it's going to be 2. We get negative 4 divided by 2, which is positive 4 over 2, which gives me 2. And so what we can do is sub 2 into our equation now. And so when we sub 2 into our equation, we just replace the x's with 2, and we get 12 minus 24 plus 6. That gives me minus 6. And so that means the vertex of this is going to be at 2 and negative 6. So we've got the zeros and we have the vertex. The last thing it said was the y-intercept. So in order to figure out the y-intercept, we really just need to look at the equation. Because for the y-intercept, it's the non-x term, because when x is 0, the only thing that stays there is the non-x term. So if you wanted to, you could substitute x equals 0 into the equation to see that that worked. That's exactly what's happening. And this is, most of us can do this in our head because it just means all the other terms, like I said, are 0. Gives me 6. So what I'm going to do now is I'm going to graph that on the grid on the right with all the information I've found. I'm just going to first give a scale here. I'm going to go up by every square being 1. So I'm not going to label every square because that might clog the graph a little bit. I'm going to label every other square. So my x-axis is on the horizontal and my y is on the vertical there, and I've labeled those. So now what I'm going to do is I'm going to label the vertex, 2, negative 6. Then I'm going to label those two zeros. They were 0.59 and 3.41. And then I'm going to label the y-intercept up there at 6. Now because of symmetry, we know that the y value will be 6 also when x equals 4. And that's because the vertex is at x equals 2, so the y values are going to be the same on both sides of that. So we go ahead and we draw our curve through those points, and we can label that with our function. That is the graphed function after finding all that we were asked. Question number 4 now says, determine the equation of the inverse of the function f of x equals 3 times x minus 4 squared plus 6 if x is less than or equal to 4. And that is very important for this question. It then says, then graph both f of x and the inverse on the same grid. So in order to determine the equation, we first let the y value be f of x. So we're just going to rewrite the equation with, instead of f of x, y. And we're going to switch x and y. That is what an inverse function does. It literally takes the x coordinates, makes them the y coordinates, and takes the y coordinates and makes them the x coordinates. So we now want to rearrange this equation for y. In order to rearrange the equation, we're going to use Bedmas in reverse. That's how we rearrange equations. So the first thing I want to do is I want to subtract or add something. Now in this case, I'm going to subtract 6 in order to get the 6 to the other side. So this gives me x minus 6 is equal to 3 times y minus 4 all squared. Now I have 3 times what's in brackets that follows. So I'm going to divide next. I'm going to divide by the 3. Whatever you do to one side, do to the other. That's going to cancel out the 3. And then I'm going to be left with just the y minus 4 squared on the right. Now I'm going to do that exponent. I need to get rid of the squared. So I'm going to take the square root of x minus 6 divided by 3. And it's actually going to be the positive or negative of that. And I'm still left with what was in the brackets, the y minus 4. Now, why is it positive or negative? Well, let me give you a simple example to consider. Consider y equals 9. Y squared equals 9, in fact. So if that was the case, then you could tell me that y could be either positive or negative 3 in order to be 9 when you square it. And so the same rationale works here. It's really just taking the positive or negative of the square root of 9. And that's what we're doing on the left side. So now we work at the brackets, which was y minus 4. And so we're going to add 4. And whatever you do to one side, you do to the other. I'm going to add 4 before the square root. It's just going to make it a little more clear to see that. So I would always do this when you do a inverse function. Always that last step of adding or subtracting the value, put it out in front of the radical. So we've got 4 plus or minus the square root of x minus 6 all over 3. Now keep in mind, the original function had a restriction that said x had to be less than or equal to 4. And because the inverse switches the x and y values, that means the inverse has to have a restriction on y. Y has to be less than or equal to 4. Well, in order for that to be the case, I can't add anything to 4. I could only subtract. So the inverse function is only the subtracting part of this, not the adding part of that. It's just 4 minus the square root of x minus 6 all over 3. And let's go to the graph and see how that plays out now, because it asked us to graph both on the same grid. What I'm going to do first with that is I'm going to go ahead and I'm going to make a scale. Every square is 1, but I'm not going to label every one again just so that I don't clog the graph. There's my x and y axes. And I'm going to start by graphing the original function. The original function had an a value of 3, and it had a vertex of 4, 6. So the a value is 3, positive 3, which means that it opens up, and the vertex was 4, 6. So let's go ahead and let's start by graphing the vertex of 4, 6. And then we have the restriction that x had to be less than or equal to 4. Well, that's only the left side of that quadratic. You see, I've continued it kind of like with a bit of a dotted line, but it actually only exists on the left side due to the restriction. So what we're going to do now is when we go to graph the inverse function, rather than trying to graph something with a radical in it, we're going to use the property that the x and y coordinates just switch. So the vertex of the original function f of x was 4 and 6. So that means that the coordinates of the vertex of the inverse function is going to be 6 and 4. And so swapping those around gives me that. And then also we had that y had to be less than or equal to 4. So it's the bottom half of a sideways parabola that opens from the point 6, 4. Now if you take that maybe one step further still and you draw the y equals x line all the way up on the diagonal, you should be able to see that what's happened is the parabola has flipped exactly over the line y equals x because the x and y coordinates have switched. So there you go. Number 5 says find all possible values for k if there's only one 0. F of x equals kx squared plus 8x plus k minus 4. So what would we substitute in for the both cases with the k in order to make that have 1, 0? Well, to have 1, 0, remember that the number of zeros is based on the discriminant. The discriminant is the value that's under the square root in the quadratic formula. So the b squared minus 4ac, if that's bigger than 0, has 2 zeros. If that's equal to 0, there's only 1 0. And if it's less than 0, there's actually no zeros or 0 zeros. Now in this case, we have the situation where it's going to have 1 0. And so just remember there's the quadratic formula. And so it's that value that's under the square root. And if we have nothing under the square root, then we're not adding anything to negative b over 2a. And so that's why it just gives us 1, 0. So let's go ahead now and try to solve the b squared minus 4ac equals 0 case. We set that up first, and then we recognize what a, b, and c are. The a value is k. That's the value in front of the x squared term. The b value is 8, the value in front of the x term. And then the k minus 4 doesn't have any x with it, so those together are the c value. So what we go and do is we sub those into the b squared minus 4ac, and we get 8 squared minus 4 times k, a was k, and c was k minus 4. So what we need to do now is we need to expand this out and try to solve this. So 8 squared is 64, and then 4 times k is 4k, and then we still have the k minus 4 in brackets. Expanding this out one more step further, it gives me 64 minus 4k squared, and then the negative 4k times negative 4 gives me positive 16k. We are left with a quadratic. Who would have thought? So we're going to rearrange this now so we can clearly see the first term with the a and then the b and then the c. And we're going to go ahead and common factor a negative 4 out of that. So we get negative 4 times k squared minus 4k minus 16. And what we hope is that we can go ahead, once dividing by negative 4, and factor that. You can go ahead and try that, but unfortunately, it's not factorable. And that's why we have the quadratic formula that I've already listed on the right side. Now notice here that what we're trying to do is we're not trying to solve for x, we're trying to solve for k. So I'm just going to rewrite this instead of x, I'm going to write this as k equals those values. But we're going to go ahead and substitute the b value is negative 4, and then the a value is 1, and the c value is negative 16. It's very important you get the sign right. Otherwise, this is not going to be possible to solve. So we get k equals 4 plus or minus the square root. Negative 4 squared is 16. And then negative 4 times 1 times negative 16 gives me positive 64. So that's going to ensure that the value under the radical is a positive value. Otherwise, we couldn't actually find the square root, and it wouldn't have any solutions. Any real solutions, that is. Now, the root 80 is the square root of 16 times 5, and the square root of 16 is 4. So I can rewrite this as 4 plus or minus 4 times the square root of 5 all over 2. And now I want to common factor 2 out of this so that I can get rid of the 2 in the denominator and make that not a fraction anymore. And so now I can cancel out the 2 in the numerator and denominator, and I get 2 plus 2 root 5, or 2 minus 2 root 5. And so those are the exact solutions that are going to make 1, 0 here. And so if I take that and I sub that in for the 2 places the k value is in the equation up top, that will ensure that I have exactly 1, 0. Not a pretty number, but it's going to work exactly right. Unit 4 is all about exponential functions. We're going to solve 3 problems here. First, looking at how to apply the exponent laws. Then we're going to look at an exponential decay application. And finally, look at the function on the right and list all the properties shown. This question says simplify using exponent rules. Now, the first question you might have is, what are the exponent rules? Well, I'm so glad you asked. The first one is the product rule. If they have the same base and they're multiplied, we can add the exponents. If they have the same base and they're divided, we can subtract them. That's the quotient rule. The power of a power rule says that we take the power outside and multiply it by the power inside the brackets. The power of 0 rule, anything the power of 0 is 1. Negative exponent is the reciprocal. And the rational exponent law is we take the nth root of something if it's in the bottom of a fraction that the exponent's raised to. So here's the strategy we're going to look at. We want to look inside to outside the brackets. That's the first thing for these questions. And the second thing is we're going to use the negative exponent law at the very end and only at the very end. Otherwise, you're going to be flipping things a lot, and it's going to make your life a lot more difficult. So only at the very end are we going to use that. So let's go and dig into this first one and apply this. So the first thing we're going to do here is working inside to outside. We're working on these inside brackets. So 7 to the power of 2 divided by 7 to the power of negative 1. Well, we're going to use the quotient rule. 2 minus negative 1 means we add 1. And so we can simplify inside those brackets to be 7 to the power of 3. Now that's all to the power of negative 2. So now we can use the power of a power rule. 7 to the power of 3 times negative 2 gives me 7 to the power of negative 6. Now the quotient rule we're going to use again. Because we're dividing, we're going to subtract those exponents, and we can only do that because they have the same base. So 7 to the power of negative 3 minus negative 6 means you add 6, gives you power of 3, and 7 to the power of 3 is 343. Now, 7 to the power of 3 is the final answer because it didn't tell us to get a final answer, it just said simplify. The second question, we're going to use the same idea, but we're going to have a little bit more with the rules applying here. The first one is the power of a power rule. 12 times 0.25 is 3, so x to the power of 3. And then everything else in the numerator is going to stay the same. Now, notice that the power of a power rule has the 6 applied to the 3. That's what my students miss the most. And the x. So 3 to the power of 6, x to the power of 6, and then x to the power of 9 at the end. And that's all to the power of negative 1/3. So now what we're going to do is we're going to apply the product rule by combining the powers of x in the numerator and in the denominator. So 3 plus 9 gives me 12 in the numerator, and then we have 6 plus 9 gives me to the power of 15 in the denominator. Still all to the power of negative 1/3. And you'll notice as well, I have not expanded out the 3 to the power of 6 because I'm going to look at that negative 1/3, and that'll likely simplify something for me. So I'm now going to apply the quotient rule, so 12 minus 15, so that gives me x to the power of negative 3. And the last thing now I want to do now is bring that negative 1/3 in. And again, I'm keeping that 3 to the power of 6. I'm not expanding that and simplifying it with the 216. You could do that, but I'm going to do that the way I'm doing it just to make the numbers a little smaller that I deal with. And that I like that, keeps it a little easier. So we go ahead and we multiply the negative 1/3 times 1 for the 216 times negative 3 for the x to the power of 1. And then we get negative 6 over 3 for the power of 3. Now that means I'm going to apply the negative exponent rule to the two numbers. I'm going to bring the one that's in the denominator to the numerator and the one that's in the numerator to the denominator, and then apply these. So 3 to the power of 6 over 3 is 3 squared, and 216 to the power of 1/3 is the third root of 216. 3 squared is 9, and the third root of 216 is 6. So I can simplify that to be 3x over 2 by dividing the numerator and denominator by 3. And so we've applied all the rules but the power of 0 rule. That's how it works. This question says the population of tigers in Africa has an exponential rate of decay of 5% every year. Notice it's a rate of decay. We'll come back to that in a moment. If the tiger population in Africa was 25,000 in 2019, how many tigers will there be in Africa in 2040? And then in what year will the tiger population become half of what it started at in 2019? So the first thing to keep in mind here is the general equation for exponential growth or decay. It's the population after some time is equal to A times B to the power of T. Now A is the starting population or the starting value. That's pretty straightforward here. It's going to be 25,000, which we'll sub in here in a moment. B is a little more tricky, and what we have to do with this is we have to recognize that this is the exponential growth or decay factor. It's essentially what I'm multiplying by each year to get the number I have the next year. So for an exponential growth, what I'm going to do is it's going to be 1, B is equal to 1, plus the growth rate. Now that growth rate has to be listed as a decimal. If it's not as a decimal, then it's not going to be correct. So for example, if you had a 5% growth rate, you list it as 0.05. If it's decay, we're going to write it as B equals 1 minus the decay rate. Now in this case, the decay rate is what we have because it's becoming less every year. And so we write that also as a decimal. So in this case, what we're going to get is 1 minus 0.05, which is going to give us 0.95 in our specific case. So the population after some time is equal to 25,000. That's our starting value, 25,000. And then we're going to substitute in 0.95 for B, as I already mentioned, because of that decay rate of 5%. 1 minus 0.05. So we subtract that and we get 95%. That's what that means. It's really, I'm going to have 95% each year of the population I had the previous year. So 0.95 to the power of T. Where T, and we have to be specific here, it's the number of years. Sometimes with bacteria or things you might have number of minutes or hours. But here's the number of years, and specifically since 2019, because that's where we're starting this equation off at. So we have to be very specific with how we define our T value. And so our P is our population of tigers after T years since 2019. So the first question is, how many tigers will there be in Africa in 2040? So now that we set up our equation, we can actually solve that. We take the 2040, we subtract the starting year, we get 21 years, and all we have to do is substitute that into the equation. Really, really simple substitution. You can type that in your calculator. You go 0.95 to the power of 21. Be careful that you don't multiply the 0.95 times 25,000 first, because if you did and you got an answer for that and then put it to the power of 21, it would be a lot bigger number. So just the 0.95 to the power of 21 and multiply that by 25,000. We get 8,514 tigers. We round that number and we can't have part of a tiger. So there's going to be 8,514 tigers in Africa in 2040, according to this model. This isn't actually true, but this is a model that someone might have. So now it says, in what year will the tiger population become half of what it started at in 2019? Well, half of what it started at is 25,000 divided by 2, which is 12,500. And so we're going to go back to our equation that we had. Population after some time is 25,000 times 0.95 to the power of T. In this case, we don't know what T is, but we do know what that P of T is, that population value is. It's 12,500. So I'm replacing the P of T with 12,500. And I'm going to try to rearrange the equation to solve for T. Now the first thing we have to do if we're trying to rearrange this equation is we have to multiply or divide first. We want to deal with the exponent last. So we're going to divide here to cancel out the 25,000 from the right side. And I get 0.5 or 1/2 on the left side. And so 0.5 is equal to 0.95 to the power of T. And here's where we can use logs. Logarithms are really helpful because when we take the logarithm of something, what it does is it takes the exponent on the one number and it brings it out in front of the log. And so what we're going to do is we're going to write this as log 0.5 equals, we can write this as T times log of 0.95. Now we can divide by everything except the T on the right side, and I get that canceling out the log of 0.95. Now on the left side, I get log of 0.5 over log of 0.95. Don't cancel out the logs. They have to operate on the number that follows. And if I do that properly, I get 13.51 years. Now, remember it's asking for what year the tiger population will become half of what it started in. I'm going to assume that the 2019 population is right at the beginning of the year. So 13.51 years later, after 2019, is 2032 and then 0.51 of that year. So that would be the year 2032. This question asks, for the third function f of x equals negative 3 times 2 to the power of 2x plus 4 plus 1. Determine the following showing all steps. Now the first thing is the parent function. Well, that's pretty easy to identify because you just identify what the b value is, what that base is. In this case, it's 2. So the parent function is f of x equals 2 to the power of x. For the y-intercept, we let the x value be 0. We just substitute 0 in and we solve the equation when that's the case. So negative 3 times 2 to the power of 2 times 0 plus 4, all plus 1. Now, a lot of people assume it's just going to give an answer of 1, but follow the math. Make sure you're actually getting this, because even though it's 2 times 0, you still have the 4 as the exponent on the 2. So that gives you negative 48 plus 1, which is nowhere near 1, as you can see. This is negative 47, not 1. So be careful assuming that it's just going to be 1. Yes, the asymptote is going to be at 1, as we'll do now, but it doesn't mean that the y-intercept will be. So y equals 2 to the x. That's our base function, or our parent function. And we would just say that has an asymptote at y equals 0. It literally goes down to 0 for that. But if it has an asymptote now up at 1, it's been shifted up 1, then that means that's our new asymptote. That's all we have to look at, just that c value that shifts it up or down at the end. And so y equals 1 is the asymptote. Part D says what the domain and range are. And so for any type of exponential function, the domain is always all the possible x values. So x is a set of all real numbers. The range, though, is something we have to think a little bit about. So if it was y equals 2 to the power of x, then our range would be y is greater than 0. If it was negative, as we can see the a value, the leading value is negative, that's going to flip it over the x-axis and make it go down. So it would be below 0. But because the asymptote has been shifted up to 1, it's going to be below 1. And so there we say y is a set of all real numbers such that y is less than 1. Doesn't touch 1, it's less than 1. Now part E says sketch the graph. And there's a couple of ways we can go about doing that. The first thing I want to discuss is just how do you do that with transformations. So remember that the general form of an exponential function is f of x equals a times b to the power of k bracket x minus d. We common factor out the k value so we clearly see where the d value is properly, plus c. And so I'm just going to rewrite that equation I had at the top with that k value factored out so that we can see that the d value is not 4 or negative 4. It's actually negative 2 here, as we'll discuss in a moment. The a value is negative 3, which is a vertical stretch factor of 3. And it also being negative is going to flip it or reflect it over the x-axis. And so we could take any points from the equation y equals 2 to the power of x, and we can apply these transformations through this. So if k value is 2, that's a horizontal compression. And the reason it's a compression is because the factor for the k value is always 1 over the k value. So it's 1 over 2. The d value is going to be negative 2 here because it's x plus 2 means if the general form is x minus d, it's x minus negative 2. That makes it plus, which means it's going to shift it 2 units left. And then the c value is 1, which means it shifts 1 unit up, as we've already discussed with the asymptote. So what you could do is you could take a couple of points. For example, we could take the point 0, 1. That's the point, always the case for any exponential function that hasn't been transformed. And 2, 4. Those are 2 points that are on that original graph of y equals 2 to the power of x. You could then take the y values and multiply them by negative 3, because that's what the a value is doing. Then you could take the x values and multiply them by a half. That's what the k value is doing. And then the d value is also operating on the x value, so you subtract 2 from that x value. And the c value would be adding 1 to the y value you had from before. So in general, what we're doing is we're taking the coordinates x comma y, and to the x coordinate, we're applying 1 over k to it, and then we're going to add d, whatever d is. And to the y coordinate, we're multiplying it by a, and then we're adding c to that. And that's going to give us the final coordinates, and we could translate all those coordinates like that. But I would ask the question, what are the most meaningful points on this graph? What are the things we care the most about? Because it might not be those points that we transform. They might not be much of interest to us. The ones I would argue are the most important are starting with the y-intercept. That's by far the most important. We know that's y equals negative 47, which if you translate 0, 1, and 2, 4, you're not going to get that by translating that. The other key thing we want to look at is the asymptote y being 1. And so because of that, I'm going to go up and down by a scale of 10, and I'm going to go with an x scale by 1. And I'm going to label my asymptote at y equals 1. And so I know that it's coming from below. It's going to go through negative 47. It's going to look something like that. So what I want to do just to get a better sense of the shape is I want to substitute in a couple of x values that are just to the left of that y-intercept. So I'm going to substitute in negative 1. And when I substitute that in, I get 2 to the power of negative 1 plus 4 as the exponent. And so I get 2 as the exponent, which gives me negative 11. And then if I sub in negative 2, I end up getting, after subbing in, negative 2. So what I can do is I can label those points on my graph. And you can actually see that that's a lot steeper than I originally labeled those curves with. So it's going to go up through those key points. It's going to be a very steep graph like shown. And we can label that with the function f of x equals negative 3 times 2 to the power of 2x plus 4, all plus 1. Unit 5 is all about trigonometric ratios. We're going to use SOHCAHTOA, we're going to look at the special triangles, learn how to use the cast rule and apply it, prove trig identities, and solve three-dimensional trig problems. If we're asked to find the following exactly, we need to first remember SOHCAHTOA. SO stands for sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tan, which we're using here, is going to be the opposite side over the adjacent side. So what we need to do is we need to now figure out what triangle we're going to use. And we're going to use a special triangle that is the following triangle. It comes from an equilateral triangle that has all the side lengths of 2, and we cut it right down the middle so that the base is 1 and the height will be root 3 by the Pythagorean theorem. So now the 60-degree angle is just above the horizontal there. And that's the angle I'm taking the tan of 60 of. So if I take tan of 60, it's the opposite side, which is root 3, divided by the adjacent side, which is 1. So it just simplifies to root 3 over 1, because anything over 1 is just the same thing. So now we move on to cosecant of 45 degrees. Now the first thing to remember is that cosecant is the reciprocal of sine. So cosecant of an angle is 1 over sine of an angle. And it's also important to remember, going back to SOHCAHTOA, that sine of an angle is equal to the opposite over the hypotenuse. So if it's the reciprocal of that, that means that cosecant of an angle is going to be the hypotenuse over the opposite side. Now what triangle we're going to use, because the 30, 60, 90 one that we have on the left is not going to work. And so this second special triangle comes from a square that's 1 by 1 by 1 on all sides. And if we cut that across the diagonal, we can see that it's a 45-degree angle. And so the hypotenuse would be root 2 by the Pythagorean theorem. So we're trying to take the hypotenuse, which is root 2, over the opposite, which is 1. So it's just root 2 over 1, which simplifies obviously to root 2. And there you go. We've looked at the two special triangles, and we've also gone over SOHCAHTOA. This question says theta is an angle in standard position with its terminal arm in quadrant 2. If tan of theta equals negative 2/3, determine exact values for x, y, and r, and then it tells us to determine the measure of angle theta and another angle between 0 and 360 that will have the same tan ratio. Well, let's think about first what quadrant 2 is. Quadrant 2 is this quadrant right here. Quadrant 1 is over here, quadrant 3 is down here, and quadrant 4 is in the bottom right corner. Now with that established, let's think about what tan is. Tan of an angle is the opposite over the adjacent. Now the negative is just going to be negative if we are the not negative x values or the negative y values. So I'm going to focus in here on the magnitudes of these values. Because it's 2/3, that means the opposite is going to be 2 and the adjacent is going to be 3. If it's in quadrant 2, that means it's going to look something like this, where this side is length 2 and this side is length 3. Now, the thing to keep in mind as well is that because it's negative, that means that one of those values has to be negative. Well, it's actually going to be this value because the x value is representative of the horizontal distance and the y value is representative of the vertical distance. So then we have x equals negative 3 and we have y equals 2. So the last value we want is the r value here because what's happened is we've turned this terminal arm from 0 right along there all the way to here. And that r value represents the length of the terminal arm. So r squared is equal to x squared plus y squared. That's all we have to do, the Pythagorean theorem for this, because that's a right triangle. So r is equal to the square root. X is -3 all squared. It's going to make it positive. Y is 2. We're going to square that. And so we're going to get the square root of 9 plus 4, which is going to give me an exact value of the square root of 13. That's approximately equal to 3.6, but that's not what it asked us for. It asked us for exact values. So those are all our exact values for x, y, and r. So that was part A. Now in part B, it asks us to determine the measure of angle theta. And so the angle theta is that angle right there, as I've already mentioned, as that terminal arm has turned from there. And what we want to do is we want to determine what that is. Now, the easiest way to do this is to think about the related acute angle here being beta. And if we just kind of get away from the coordinates for a moment and just think about the triangle that's there, we see this triangle that's 3, 2, and root 13. So we're labeling that related acute angle right in here. It's a 90-degree triangle. And so what we could say is that tan of beta is equal to the opposite, which is 2, over the adjacent, which is 3. And so to determine what this related acute angle is, we always take the positive of whatever the ratio is. And so now we can go beta is tan inverse of 2 over 3. And that tan inverse of 2 over 3 gives me an angle of 33.7 degrees. So 33.7 degrees. Well, now if I look at the diagram on the left, theta is equal to 180. And then what we're going to do is we're going to subtract the 33.7. So it's all the way around to here minus the 33.7. So when we do that, we end up with an angle for that of 146.3 degrees. Now that's the first angle. Notice I said there's always two angles, and this is the angle that's actually in quadrant 2. But we also could have the tan ratio be negative in another quadrant between 0 and 360 degrees. Let me just do that with another color on top here so that we can see it on the same axes that I drew the angle in part A on. Tan is also going to be a negative ratio in quadrant number 4. And that's because of the cast rule. The cast rule says that cosine is positive in quadrant 4, that all ratios are positive in quadrant 1, that sine is positive in quadrant 2, and that tan is positive in quadrant 3. So the only quadrants that tan can be negative in are quadrant 2 and quadrant 4. So what we're going to do is we're going to draw that same related acute angle in quadrant 4. And what we can see here, if we draw that same related acute angle in quadrant 4, is that that means that the y value would be -2 and the x value would be +3. So if I took tan of that angle, call this theta 2 all the way around to here, and we'll call the other angle theta 1, tan of theta 2, that's going to be equal to the opposite, which is -2, over the adjacent, which is 3. Same ratio, -2/3. So what we're going to do is we know it has the same related acute angle. So all I have to do for this is I'm going to say that theta 2 is equal to 360 all the way around, but then I'm going to, after I get all the way around, I'm going to subtract beta from that. And so I subtract beta from that. So that's going to be minus beta, which is 33.7 degrees. And so that's going to give me an angle of 326.7 degrees. And that is the measure of the second angle. Both of those angles are between 0 and 360. This question says, prove that 1 plus tan squared theta is equal to secant squared theta. State any restrictions on the variable. Now you'll notice here I have tan and secant. Those are trig ratios, which suggests to me that I can go back to the first principles definition of any angle in terms of x, y, and the length of the terminal arm, r. And so if I have a terminal arm, the terminal arm always is measured from the positive x-axis. It has a length of r, and the coordinates at the end of that terminal arm are x and y. And so if those are x and y, that means that the x coordinate is represented by the horizontal distance on that triangle, and the y coordinate is represented by the vertical distance on that triangle. Now, that we're going to label as theta. And what we can do here is we can say, well, tan, we know that tan is going to be the opposite over the adjacent. And so because tan is opposite over adjacent, part of SOHCAHTOA, that means that tan of the angle is going to be equal to y over x. So that's the first thing to keep in mind. Secant, though, this is a reciprocal identity. So secant is the same thing as 1 over cos. And SOHCAHTOA tells us that cosine is equal to the adjacent over the hypotenuse. And the adjacent side is x and the hypotenuse is r. So cosine of an angle is x over r. Now if secant is the reciprocal of that, that means that secant of an angle has to be r over x. So these are the definitions that we need now to do this proof with. So let's go ahead and do that. Whenever we do a proof, we go left side and we separate it from the right side. So we're going to go 1 plus tan squared theta. And the right side is equal to secant squared theta. And so this becomes 1 plus, well, tan we said is y over x. So this is going to be y over x all squared. The secant we said was r over x. So this is going to be r over x all squared. And now what we can do is we can expand and simplify both sides of this. So I'm going to get 1 plus y squared over x squared. Now, I have one term on the other side, so how do I get this to be one term? Well, if I can write this with a common denominator, that can be one term. So I'm going to write this by multiplying the top and bottom by x squared. Whatever you do to the top, you have to do to the bottom to keep the fraction the same. And what this is going to give me, it's going to give me x squared over x squared plus y squared over x squared. So this becomes, because it has a common denominator, x squared plus y squared over x squared. Now let's go back to the right side here for a moment, because if expanding this out, we get r squared over x squared. So those have the same denominator. So the only difference is the numerator. Well, look at the right triangle that we drew over here. That is, using the Pythagorean theorem, x squared plus y squared equals r squared. So this, by the definition of the Pythagorean theorem, becomes r squared over x squared. And therefore, the left side is equal to the right side. Now, the last thing this question said to do was state any restrictions on the variable. So in order to state restrictions on the variable, what we want to do is we want to look at the variables that we have here and say, are any of those ever not allowed to be 0? Well, if you go through this, we can see that we can't ever have x be 0 all these places. X can never be 0. We can't divide by 0. And so because of that, that means that x cannot be 0. And then what we do is we take that and we put it in terms of angles. Well, when is x 0? If I turn this angle all the way up to here, now the x coordinate becomes 0. And if I continue to turn it all the way down to here, the x coordinate is 0 again. Those angles are at 90 and 270 degrees. And so what we would say is that theta cannot be 90 or 270. So this identity works except for when theta is 90 and 270. This question says, using these identities, the 8 in front of us, we are to prove that cos squared theta times secant squared theta minus 1 is equal to sine squared theta. Now the key here is that if we're trying to prove any of the 8 identities at the top, we want to use x, y, and r to prove those. But for anything beyond those 8 identities, we can use those 8 identities as building blocks to prove them. So what we're going to do here is we're going to start by breaking this to the left and right side. So the left side is equal to cos squared theta times secant squared theta minus 1. And the right side is equal to sine squared theta. The reason we do that is we're not trying to manipulate the equation. We're trying to get each side to be the same thing. That's a proper mathematical proof. So the first thing we can do here is recognize that secant is equal to 1 over cos, that identity right there. And so if we write that out on the left side like that, we get cos squared theta times, well, if secant is 1 over cos, that means that secant squared is 1 over cos squared. So that it can be written like so. Now what we're going to do is we're going to expand the cos squared theta in. And so when we do that, we get cos squared theta over cos squared theta. That nicely simplifies to 1, minus cos squared theta. So we're going to write this as 1 minus cos squared theta. Well, now we can look at this other identity, a Pythagorean identity. Sine squared theta plus cos squared theta equals 1. If I rearrange that for sine squared theta by subtracting cos squared theta from both sides, I get sine squared theta equals 1 minus cos squared theta. And so now what we've done is we can write this out as sine squared theta. And so we've proven that the left side is equal to the right side, and that identity is proven. However, we are also asked to state any restrictions on the variable. And so for restrictions, what we want to do is we want to recognize there are certain x values, or certain theta values rather, that are not possible. So what we do is we look here and we say, well, when can we not divide by 0? Because for restrictions, it's all about dividing by 0. It's not allowed to be done. We can't possibly do it. It's not possible. So is there a situation where we're possibly dividing by 0? And we can see that that's when cosine is in the denominator. There's nothing else in the denominator except cosine. So that restriction is going to come in when cosine of an angle is equal to 0. Well, when is cosine of an angle equal to 0? Let's quickly just draw a terminal arm in quadrant 1. It doesn't matter what quadrant we draw it in. And then there's an y-coordinate of that point on the terminal arm, an x-coordinate of that point on the terminal arm, and then r is the length of the terminal arm. Well, this is the angle, call it theta, to correspond with what we have for the question. And now we ask ourselves, well, because it's a 90-degree triangle, when is cosine theta going to be 0? Well, cosine is the adjacent over the hypotenuse. So if cosine is the adjacent over hypotenuse, what we're really saying is when is x over r going to be 0? Well, that's going to be 0 when x is 0. Well, when is x 0? X is 0 at this angle right there, which is 90, and at this angle right here, which is 270. So we can conclude that theta cannot be 90 or 270. So this identity is always true except for those two possible angles between 0 and 360. This question says, given sides A equals 15, side B equals 20, and angle A equals 30, for a triangle, sketch all possible triangles and determine all angles. And we're then to clearly indicate how you determined if 0, 1, or 2 triangles can be drawn. Now this is about the ambiguous case of the sine law. What that means is it's the unclear case. It could be 0, 1, or 2 triangles. So how do we know? Well, how we know is we start by drawing a diagram. And how I always like to draw my diagrams is I always like to draw my diagrams where the angle that we're given is up from the horizontal like so. And so we know that that angle A is 30 and the side opposite angle A is this side A, which is 15. So I'm going to draw this as 15 here. A equals 15 centimeters. And then the other side that I know, I'm going to label that as the side that's touching angle A. So B is going to be equal to 20 centimeters. So whenever I'm given information like this, I always begin by drawing a triangle that looks something like this. The question is, will this length 15 touch that bottom side once, or twice, or not at all? And so what we want to do is we want to determine the height of this triangle. In order to determine the height, we can use a trig ratio because we're looking at this right triangle here on the left side of that diagram. And so the trig ratio we could use that uses height and uses this side B is the trig ratio sine. So sine of 30 degrees is equal to the opposite side of that right triangle, which is h, over B, which is 20. And so I go 20 times sine of 30. Well, sine of 30 is 1/2, and so this ends up being 20 times 1/2, which is exactly 10. And so because this length right here, A, that length is longer than the height, what that means is that we can draw more than one triangle. Because I could take that, suppose I fixed that right here at this point, and I swung that length A, I could swing that all the way down here and it would connect to the bottom length down there. Now remember, we don't know the length of, I guess, which is side C. And so it could be the length all the way to the dot right there, but it could also be the length only to this dot right there. That would also form a triangle like so. And so the second triangle that we have here is actually going to be this triangle right here. Same A value, same angle, same B value, that's 20 centimeters. But then instead of going down to the right, it's going to go down a little bit to the left, and it's going to form a triangle there that now has the same A value of 15 centimeters, but that angle C is going to be smaller than in the case above. So just label those vertices like so. Why is that the case? Well, this is going to be an isosceles triangle where this length here is going to be equal to this length there based on that arm swinging across. So we know that we can draw two triangles. So two triangles can be drawn. because the length of A is greater than h, but it's also less than the side length b. It has to be less than length b, otherwise when we swung that arm over, it wouldn't form a triangle. So now that we have that established, let's go about determining what the angles are. And so the first thing I'm going to do is I'm going to look at the triangle on the top left, and I'm going to try to determine what the angle is right in here. Now the reason I've chosen that one is because I know one thing of that pair, and I know two things of another pair. And so I know 3 of 4 things. That ratio will help. So I'm going to go sine of B over B is equal to sine of A over A. So let's put those in now. So sine of B, length B is 20, and then angle A is 30, and length A is 15. So if I rearrange that, I get sine of B is equal to 20 times sine of 30 divided by 15, and then I take the sine inverse of all of that to get B by itself, and so I get B to be an angle of 41.8 degrees. So what that means is in the diagram right here we have B is 41.8 degrees. Now angle C is fairly straightforward to solve from there, because angle C, well, that's just going to be 180, because all 3 angles add to 180, so it's 180 minus 30, the A value, minus 41.8 degrees. And so that angle ends up being an angle of 108.2 degrees. So we could label that on there as well as 108.2 degrees. Now, interestingly enough, if I use the sine law to determine what angle B is over here, I'm going to get 41.8 again. And this is the ambiguous case of the sine law. It's not going to give me the answer I actually want, because that's clearly bigger than 90 degrees. Now the key here is that the fact that this is an isosceles triangle that's formed by that arm, length A, being swung from the one place across to the other. And so what we need to recognize is that this angle in here is 41.8, and then that means that this angle in here is 41.8 because it's an isosceles triangle. So the angle right in here is going to be 180 minus 41.8. 180 minus 41.8 is an angle of 138.2 degrees. So angle B is 138.2, and then by the same rationale as before, C is going to be 180 minus angle A, which is 30 degrees, minus the 138.2 degrees, and we end up with an angle C of 11.8 degrees. And so we've drawn and solved all the triangles. That is the ambiguous case of the sine law, and there's 2 possibilities, even though the calculator only shows you 1. This question is all about understanding the words and how they translate to the diagram here. This is a 3-dimensional trig problem that we're going to set up and then we're going to solve. We're going to walk through the steps of how to set it up and then walk through all the steps of how to solve that. So let's get into it. The question says 2 boats A and B, leaving the same location, travel in different directions. That doesn't mean they're traveling opposite each other. That just means different directions. After some time, a person standing on an observation deck above where the boats left sees boat A at an angle of depression of 22 degrees and a bearing of 140 degrees. At the same time, the person sees boat B at an angle of depression of 28 degrees and a bearing of 212 degrees. If the observation deck is 100 meters above the water, how far apart are the boats? Well, the first thing we need to get a handle on here is what bearings are. And so bearings are relatively simple. We start at 0 degrees being straight north, and then we turn around in a clockwise direction. So 90 is there, 180 is there, 270, and then 360 when you get all the way back to 0 degrees again. And so the idea here is that if we're looking at the bearings of these boats, boat A is at a bearing of 140 degrees, so that's somewhere in about here. So if we're looking at from above, then what we're going to see is we're going to see boat A right in here with a bearing of 140. And then boat B is at a bearing of 212 degrees. So that's going to be somewhere in here. So boat B is at a bearing of that. And so 212 degrees is all the way around here. And so if that's 212 degrees all the way around there, then what that means is that the angle right in here is going to be the difference between those 2 angles. So the angle right in there is going to be 212 minus 140, which is going to be 72 degrees. So that's the first thing to get right. That's the top view. And what we're actually trying to determine is we're trying to determine how far apart A and B are. But we're not given enough information to solve with just that. So what we have to do is we have to look at the side view as well. And so the side view has to do with looking at the angles of depression. So boat A has an angle of depression of 22 degrees. Well, an angle of depression means this. It means that if you are standing on the observation deck, and let's say this is the person here on the observation deck 100 meters up, then what they do is they're going to look down on one side 22 degrees below the horizontal. And what they're going to see at 22 degrees below the horizontal is they're going to see boat A somewhere out there on the water. That's going to form a 90-degree triangle because that's a vertical triangle that's forming. The other boat, boat B, is at an angle of depression of 28 degrees. So that angle is slightly more, and that's an angle of depression of 28 degrees, and they're also level on the water with the other boat. So the height at which those are found is going to be the same. This is 28 degrees. Again, that's a right triangle because we're looking at that side view. Now we could use the Z pattern, and we could say that this is 28 degrees and this is 22 degrees. And so we have a horizontal picture, and we have a picture from above. And what we want to do is we want to put those two together. Now, I already said that the fact that they're traveling in different directions, that does not mean that they're exactly 180 degrees from each other. As we can see from above, they're actually 72 degrees from each other. So what we want to do by putting these two diagrams together is we want to fit them on top of each other. So in other words, the diagram that we see the horizontal picture of, we're kind of going to bend those in so that it looks something like the following. Here is the 100 meters, and then we have an angle down to boat B, and then we have an angle down to boat A, and we're trying to find the distance between boats B and A. So straight across like so from B to A. Now recognizing that these are the two vertical triangles, I'm going to label this C down here and D up there. So BCD is a vertical triangle and ACD is a vertical triangle. But this triangle ABC is, with this angle of 72 degrees here, that is the triangle that's flat along the surface of the water. So I'm just going to add these 28 degree and 22 degree angles as well. And now we can start trying to solve this. So here's where I would suggest a very helpful technique. It's called I could find if I knew. I could find if I knew. So we're going to write I could find, and we're going to make a plan backwards, as you'll see, to make a solution or find a solution for this. So I could find AB. Well, what do I need to know? Well, I know the 72 degree angle in that triangle, but I don't know any lengths. So I need to know BC and I need to know AC. So if I knew BC and AC, well, how do I find BC? Well, I found BC because I could find that if I knew, well, I know an angle and a length in that triangle. So I need to know angle B and length CD. Do I know that? Yes. So I can solve BC. It'll be the same rationale for AC. I'd need to know AC if I knew angle for AC. I would need to know angle A and the length CD as well. And so I know that as well. And so what I'm going to do is my plan is this. I'm going to start by finding the length of AC. The second step I'm going to do is going to be finding the length of BC. And then I'm going to add those together using the cosine law to find the length of AB. So let's go ahead and carry out those steps. But let me just move the diagram over to give us a little bit more space. So step one, if we're trying to find the length AC, we're going to say tan of 22 is equal to the opposite side. Well, that's going to be this length CD divided by the length AC that I'm trying to determine. So tan of 22 is equal to CD is going to be 100 divided by AC. And now what I can do is I can multiply both sides by AC. That brings the AC up. And then I can divide both sides by tan of 22. So effectively what happens is I'm going to switch the place of tan 22 and AC. So AC is equal to 100 divided by tan of 22. And so what I get for AC is I get a value of approximately 247.5087 meters. Now I'm going to keep lots of extra decimal places because it's important for accuracy as we take that value and calculate other things with it. So now step 2. We're trying to find the length of BC. Well, that's going to involve tan of this 28-degree angle. So the opposite side there is CD, and the adjacent side is going to be BC. So tan of 28 is equal to CD divided by BC. CD is 100. And so what I can do is I can rearrange it just like I did the previous one in order to solve what BC is now. And so BC ends up being equal to 100 over tan of 28, which is a value of 188.0726 meters. And so that should make sense that BC is closer than AC because the angle of depression was greater. So now the final step is now bring all this together using the cosine law. The cosine law. Now the cosine law can be written as c squared equals a squared plus b squared minus 2ab cosine of angle C. Well, how does it apply specifically to the triangle on the bottom? Well, I'm going to be careful here because angle C can actually be one of 3 angles. Because C is this vertex here, it could be this angle, or this angle. So instead of just using one angle for each of those lengths, I'm going to use one letter for each of those lengths. I'm going to use 2 capital letters with a bar over top of them to represent the lengths. So let's go ahead and do that. So the length C, that's AB that I'm trying to determine. So AB squared is equal to the length of AC squared plus the length of BC squared minus 2 times the length of AC times the length of BC times cosine of angle C. Well, angle C, I guess that's angle ACB here. That's 72 degrees. And so we could just label that as angle ACB. So let's put the numbers in and go ahead and solve this. AB, I'm going to have to take the square root of everything on the right side in order to get AB by itself. And so AC, we know that AC is a length of 247.5087. We're going to square that. We're going to continue that pattern with 188.0726. Going to square that. And then subtract 2 times each of those numbers. 247 point goes on from there. And 188.0726, it goes on from there. Just for the sake of space, I'm just going to write ... there. And then cosine, and the angle that we're taking is 72 degrees because that was the angle between the 2 bearings. And so when we get that calculation, we need to make sure that we go 2 times 247 times 188 times cosine of 72 before we subtract it from the other values. That's a common mistake I see people make. They subtract the numbers in front of the cos 72 before multiplying it by cos 72. Remember to multiply it by cos 72 first. And so if you do, you get a value of 353.6 meters. And what that means is the boats, A and B, are that far apart. Boats A and B are 353.6 meters apart from the observer. That's what they're able to calculate based on what they observe. Unit 6 is all about sinusoidal functions. We're going to look at how to graph sine x and cos x, and then how to apply transformations to graph a transformed function and how that applies in real life. This question says state the transformations in the order that you would apply them required to graph the sinusoidal function shown. Describe what this does to the amplitude, period, starting point, and equation of the axis. Graph the transformed function. The first thing we want to do in order to understand how to graph this and transform it is to remember what the cosine function looks like. That's the parent function here that we're transforming. The cosine function has an amplitude of 1 and it has equation of the axis at 1 and a period of 360, and it looks like that. So what we're going to do is we're going to apply the transformations that are in the equation to that cosine function. It's also good to keep in mind what the sine function looks like. We're not going to use that here, but it is very similar to the cosine function, and it looks like what you see there. It has an amplitude of 1 as well, and a period of 360, and an equation of the axis at 0, but you'll notice that it starts at the equation of the axis and goes up from there. So let's compare this now to the transformed function. So in general, the transformed function is y equals a times cos of k x minus d plus c. So a is -4, which means it's a vertical stretch by a factor of 4. In other words, we're going to take the y values and multiply them by 4, but it's also negative. So not only are we going to multiply it by 4, we're going to multiply those y values effectively by -4. We're going to vertically stretch it by 4 and flip it over the x, the horizontal axis. The next thing to look at is the k value. And the k value here is a third. What that means is that we are going to do a horizontal stretch or compression. Now the tricky thing about k is it's always the reciprocal. So let's figure out what the factor is here. It's the reciprocal of 1/3, which is 3. So that means it's going to be a horizontal stretch. Horizontal stretch factor of 3. So instead of a period of 360, it's going to have a period of 1080, which we'll get to shortly. The d value is 120. It's positive because notice it's x minus d, x minus 120 up above. So that's a positive 120, which means it's going to shift positive 120 degrees to the right. And the last thing is the c value. The c value is just 1, which means it's going to shift the whole graph up by 1. So with all that in mind, let's go ahead and talk about the amplitude now. The amplitude of this function is going to be equal to 4. That's directly related to the a value. It's the magnitude of the a value. We'll deal with the negative shortly, but the amplitude is going to be 4. The period, I already alluded to, is the normal period of 360 multiplied by 3. Well, why is it multiplied by 3? Well, the period and the k value are reciprocals of one another. So effectively, you're taking the 360 degrees, you divide it by 1/3. That's the same thing as multiplying that by 3. And so that gives you a period of 1080 degrees. So there's your period and your amplitude. And so now let's look at the starting point. Because it shifted 120 degrees to the right, what that means is that it's going to start at 120 degrees, but keep in mind it's flipped over the x-axis. It would normally start at a maximum, and so because of that, it's going to start at a minimum at 120 degrees. The last thing is the equation of the axis, and that comes from the c value that shifted it 1 unit up. The normal cosine function has an equation of the axis y equals 0. This has an equation of the axis y equals 1. So we have all those properties now, and we're going to work together to graph this. Now, we could graph this using normal transformations, just like shown in front of you. But what we're going to do here is we're going to allow this to show us how to create a box that is going to fit exactly one cycle, exactly one period. So we're going to start at 120 degrees, and that period is going to end 1080 later, so it's going to end at 1200 degrees. So you can see there that my scale on my x-axis just is not going to fit. So what I'm going to do is I'm going to go ahead and change that scale to make it a little better to fit the numbers here. So I'm going to go every 3 squares is going to be 120 degrees. So it goes 360, 720, 1080, and 1440. And so I'm going to start by drawing my vertical values of the box. So my c value is is 1. So that means the equation of the axis is y equals 1. And in order to make this fit, because I'm going to go 4 above and 4 below that, I'm going up by every square being 2. So I'm going from 1 to 5 because my amplitude is 4. So that's going to be the amplitude above the equation of the axis. And then I'm going from 1 down to -3 because that's my amplitude below the equation of the axis. And so I'm just drawing those as dotted lines. And the top line is going to be the max. The bottom line is going to be the minimums. And then that middle line is the equation of the axis. So now I'm going to add the horizontal values. I know it starts at 120 degrees. It's 1/3 of the way to 360. And it's going to end at 1200 degrees. It's 120 past 1080. And so that's the beginning and the end of my cycle. And so the reason we call this the box method is what you see highlighted in front of you. That is a box. And that is going to fit exactly one period inside that box. So what we have to do with that box is we have to split it in half. We have to find the midpoint of that box, which is 60 less than 720 there. So it's going to be at 660 in that case. And then we have to split that up, and you can do that based on squares or based on degrees. What I'm doing here is I'm seeing that there's 9 squares from the beginning to end. So then 4.5 to the middle, and then 2 1/4 to each of the other quarter parts of this function. The key to remember is that every period has 4 quarters to it. And so if it's starting at a minimum, then it's going to go to the equation of the axis, is going to the maximum, back to the equation of the axis, and then back down to the minimum. And I can draw my curve through all those points. And what I have is I have exactly one period of that function, y equals -4 times cos of 1/3 x minus 120 plus 1. The key to keep in mind here is that I'm graphing all this in degrees. And so if you're doing this in radians, it's the same idea, but we just keep in mind that instead of 360, we have 2 pi on the x-axis. This question says, determine the new coordinates of the point 7, 0 after a rotation of 235 degrees about 0, 0. The first thing to remember is that we always start any angles at the positive x-axis and we go in a counterclockwise direction around. So 235 is between 180 and 270, and we can draw it in that quadrant like shown. So what we're doing is we're taking a line that started at the positive x-axis and it had an endpoint of 7, 0, which means that that length of the line is 7, and we're turning it all the way around into this quadrant down in the bottom left. That's going to have the same length of the line, of that terminal arm we call that, and so that's still going to be 7. And what we're trying to do is we're trying to figure out the coordinates of that point at the end. Well, notice that this forms a right triangle and we have an x and a y coordinate. Now they're both going to be negative here because the x value is negative and it's also below the x-axis, so the y value is negative. So what I'm going to do is I'm going to call this angle here the related acute angle. And this forms a right triangle down there in the bottom left quadrant. And so in order to find what beta is first, I'm going to take the 235 degrees and I'm going to subtract 180, and I get an angle of 55 degrees. And so now what I have to do is I have to go ahead and think about what this is in terms of a right triangle. And I'm just going to take the right triangle that we have and just bring it over by itself so we can focus in on that right triangle. So that we know the angle is 55 there, and we know that the length of the hypotenuse is 7. Now, sine of that angle, the related acute angle beta, is going to be equal to the opposite side, the y coordinate, and we're going to focus in on the magnitude of the y, so just the value. We're going to not worry about the negative part right now, divided by the hypotenuse, and the hypotenuse is r. So we rearrange this by multiplying both sides by r, and we can sub those numbers in. We have 7 as the r value and 55 is the beta value. And so that tells me that the length of y, the magnitude of y, is 5.73. So if we go back over to our picture on the left, we know that's a negative value, so it's negative 5.73. Again, now focusing on that triangle that we have in black there, we take the cosine of that related acute angle, and that's the adjacent, which is the length of x divided by the hypotenuse, which is r. So we rearrange that for the length x. We sub the numbers in, 7 times cosine of 55, just like we did previously, and we get the length of x to be a length of 4.02. So now we go back to the diagram on the left, and we recognize that that x value is not just 4.02, it's negative that. And so we label that, and we can now list our point. The point is the x value followed by the y value. So it's negative 4.02, comma, negative 5.73. And that's all there is to it. This question says 2 white marks are made on a car tire by a parking meter inspector. One mark is made on the outer edge of the tire. The other mark is made a few centimeters from the edge. That doesn't mean 3. We have to interpret it based on the graph that we see there. The two graphs show the relationship between the heights of the white marks above the ground in terms of time as the car moves forward. Based on the graph, fill in the chart. Well, the first thing to keep in mind here is that the black mark, this is the mark 1, is going from 60 down to 0. And the other mark, mark 2, is going between 10 and 50. And so when we go ahead and we write the diameter of the circle the mark makes, the mark 1 goes from 0 to 60, so that's 60. And then the other mark going from 10 to 50 is going to be 40. Now the equation of the axis is the same for both of those. It's the center of the wheel. And so that's going to be at a height of 30 centimeters because the outer edge is going to go up to 60 and all the way down to 0. 30 above and 30 below that. So that's going to be the same for both of those marks because that's the middle of the wheel. The next thing is looking at the mark radius. So how far it is from the center of the wheel, the equation of the axis, up to the max or down to the min. And so in the case of mark 1, it's 30 centimeters. In the case of mark 2, it's 20 centimeters. Now we look at the period that this takes to go all the way around. Well, you can see that regardless of what function it is, they have the same period because they're going to take the same amount of time because they're at the same point on the wheel to go all the way around. So the period is 0.25 seconds to get from a minimum to a minimum, and then another 0.25 seconds to get the next minimum, etc. The circumference that the mark travels is going to be different because the inside mark is going to go less distance than the outside mark. But the circumference is always measured by taking pi and multiplying it by the diameter. So pi times 60, we end up getting a value of 188.50, and that's units of centimeters because this is a height of the mark in centimeters. And to calculate the circumference of the second mark, the diameter of that was 40, so pi times 40, which gives us 125.66, again, units in centimeters, 125.66 centimeters. So now we go ahead and we figure out the speed of the mark. Well, how do you find the speed of anything? Well, speed is simply distance over time. We see that driving down the road. We see kilometers per hour, so distance over time. So that means that if I'm finding speed in this case, the distance I can think about is the circumference because that occurs every period. That's a distance, circumference, and the period is a time. So I can make my speed my circumference divided by my period. So my circumference is 188.5 divided by a period of 0.25. And it's important to keep the units in mind here as well. It's centimeters per second. And that's going to give us 754 centimeters per second. 754 centimeters per second. Now to change centimeters to meters, we could divide by 100. And so this would give us 7.54 meters per second. We do the same calculation with the second mark. And because it's more inside on the wheel, it's going to move slower. So we have a circumference that's smaller divided by the same period as the other value. And so we end up getting a value of 503 centimeters per second. 503 centimeters per second. Again, 5.03 meters per second if you were to do that. So the thing to keep in mind here, and just it might be helpful to see a picture of the wheel. The wheel goes from 0 all the way up to 60. And then we have this, the equation of the axis is right in the middle. And then we have this mark on the wheel. And that mark is going to go around, not quite down to the ground. It's going down to 10 and it's going up to 50, down to 10 and up to 50. And so the closer you are to the inside of a wheel, just like a merry-go-round if you were on a playground as a kid, closer you are to the middle of the merry-go-round, the slower you're going, because if the further out you go, the more distance you have to travel, the bigger circumference in the same amount of time, the same period. And so that's why the speed of that inside mark is going slower, has less ground to cover in the same amount of time. So if you're ever on a playground again and you're on a merry-go-round, if you want a thrill, go as far to the outside as possible. If you're not up for thrills, either don't get on or go close to the middle. Unit 7 is all about sequences and series. We're going to look at both arithmetic and geometric sequences and series, an example of each of those. Then we're also going to look at Pascal's triangle and how the binomial expansion is developed using those coefficients. This question says the sixth term in an arithmetic sequence is 74 and the seventh term is 71. Find the 50th term. So the first thing we have to do is recognize this is an arithmetic sequence. An arithmetic sequence means that it's a type of sequence where you have some starting value and you are adding a difference to that every time. So we'll call that difference that we're adding a d value. So the second term has the d value added once, the third term has the d value added twice, and in the example that you see in front of you, we're adding 2 every time. So what that means is that the d value here is 2, and the a value, the starting value, is 1. So with those two things in mind, that's one example of an arithmetic sequence. Geometric sequences, on the other hand, are sequences that you start with a value. We're still going to start at, and we'll call it a, but then we're going to multiply by a value every time. We'll call that value that we're multiplying by r. So the second term is that starting value times r. The third term is that starting term times r twice, so r squared. So for example, I take 1, I multiply it by 2, I get 2. I multiply that by 2, I get 4. I multiply that by 2, I get 8, etc. So my r value there is 2, and my starting value is a equals 1. So this is an arithmetic sequence, and we're going to look at the general term now of that arithmetic sequence. The general term says that it's Tn. So that means what term number it is. And then it's a, the starting value, plus n minus 1 times d. Now that n is just the number term you have here. If that's applied to a geometric sequence, then we have a times r to the power of n minus 1. So now for the arithmetic, because that's the question that we have up above, let's focus in on that now and see how that one applies. So the first thing to keep in mind is that term 6 is equal to 74. We can write that in notation like shown, and term 7 is equal to 71. The difference between those terms, because they're subsequent terms, is this later term minus the previous term. So we could write it as term 7 minus term 6, so 71 minus 74. And so what that means is that we're subtracting 3 from one term to the next, all the way through the arithmetic sequence. So now we can go ahead and we can substitute the information from term 6 equals 74 and that d value into the equation, and the fact that we know everything except a means we can solve for a. So term 6 is equal to a plus 6 minus 1 times negative 3. Now that sixth term is 74, so we can also sub that in. And so it's a times 5 times negative 3. Well, that's just a minus 15, that's equal to 74. And so if we add 15 to both sides, we can solve that for a, and we get that a is equal to 89. And so from there, now we go ahead and we revisit the Tn equals a plus n minus 1 times d, but we can substitute in the a and the d value now. So the a is 89, and the d value is negative 3. So now I know I'm after the 50th term, so if I put n equals 50 into this equation, then I can go ahead and say 89 plus 50 minus 1 times negative 3. So that 50 minus 1 gives me 49, so it's 89 plus 49. And so really what we're doing is we're starting at that 89 term, and we're subtracting 3 49 times, which should make sense because every terms that we go to after the first one goes down by 3. And so we get a final answer of negative 58. So we can conclude, therefore, the 50th term of this arithmetic sequence is going to be negative 58. If you had a geometric sequence, you would have done a very similar process. You could have taken the equation that you have there for the general term and subbed them in just the same way, but instead of adding or subtracting to rearrange the equation, you would have done some division. This question says, state whether or not the following sequence is geometric. If it is, state the general term and the recursive formula for the sequence. And it gives us the first 5 terms. So T1, term 2, 3, 4, and 5 labeled as such. So what we want to do with that is we want to go ahead and we want to divide every term by the previous term and look at that multiple. Because if it has a common multiple that's being multiplied by every time, then it's geometric. So term 2 divided by term 1 was negative 4. Term 3 divided by term 2 is also negative 4. And then if we divide term 4 divided by term 3, that again is negative 4. And then the last one we check, term 5 divided by term 4, we have to take the negative 768 and divide it by 192. And I get, again, negative 4. And so this is really helpful because it tells us, because that multiple is the same every time, therefore it is a geometric sequence. And that's always the case. Anytime we have a common multiple or a common factor between all the division statements like so, then it's going to be a geometric sequence. So therefore it is a geometric sequence since every term is multiplied by the same value to get the next value. Now what is the same value? Well, in this particular case, it happens to be negative 4. So that is what we know as the R value that we'll look at in now the general term and the recursive formula. The general term is written for a geometric sequence like this. Tn is equal to a times r to the power of n minus 1. So the n minus 1 is done before applying r to the power of that. So Tn in this case is equal to the starting value a, which is negative 3, times negative 4 to the power of n minus 1, because that r value, that common multiple, is negative 4. The recursive formula is written like so. We write it out as Tn is equal to r times the previous term, Tn minus 1. And so we can go ahead and we can say, well, this is negative 4 times the previous term. But we do need a condition here, and the condition is that we have to have a starting term. So we have to have a condition that T1 is equal to the initial term, and so that means that T1 here is equal to negative 3. So now if we were asked to find the 10th term, we're not asked to do that here, but just so you know how this would operate with this, we would do something like this. With the general term, you'd say -3 times -4 to the power of 10 minus 1. Now Bedmes says you have to do the exponents first and apply that. So the 10 minus 1 is applied, and then the -4 to the power of 9, and once you get that, you multiply it by -3, and so the 10th term is actually quite a large number, which is 786,432. If you were to do that using the recursive formula, it would take you a lot longer to do that, because what's happening there is you would have to generate the second term, then you'd have to generate the third term just by substituting in the previous value every time in for the tn minus 1 to get the next value that comes. Now that might not be useful for you, but for a computer program that does loops and does the same thing over and over again to get an answer, that's a really, really useful thing to be able to have. Determine the following: the sum of the first 5 terms of an arithmetic sequence with a first term of 3 and a common difference of 7. So the first one is an arithmetic sequence. So let's look at what an arithmetic sequence is. Well, it's something that we know it starts with 3 and then the common difference of 7. So the next term is going to be adding 7. The term after that is going to be adding 7 twice to the original term of 3. The term after that is adding 7 3 times. And then the final term, the 5th term, is going to add 7 4 times to that original 3. So we could calculate this fairly easily without any equations or anything because it's just the first 5 terms. So it's 3 plus 10 plus 17 plus 24 plus 31. We add 7 every time and we generate those 5 terms. Adding them together gives us a total of 85. Now that seems all simple, but what if I was to ask you for the first 100 terms of that arithmetic sequence? That's going to take you a lot longer to do. So if there were more than 5 terms, what should we do? So let's have a look at that now. The first thing to notice is that we could set up a general equation for this. It's really saying the a term, that's the starting term, plus the a plus the difference term. The third term is a plus twice the difference term, all the way to the very end when we have a plus the difference term times the n minus 1. So if I have 50 terms, I have 49 difference values I've added to that, for example. So if I write that out like so, that's a sum of a sequence like so. But then if I write that same thing backwards below it, so I'm starting with a plus n minus 1 times d, and then I go to the next term would be n minus 2 times d, the next term would be n minus 3 times d added to the a. If I do that same thing and I add all those together and I line them all up, if I add vertically, and I add the a plus n minus 1 times d, the first 2 terms there, I get 2a plus n minus 1 times d. If I do that with the next 2 sets of brackets that are lined up on top of each other, I get the 2a plus n minus 1 times d again. In fact, I get it every single time I add up these numbers together. And so what we could say is, in general, we have this 2a plus n minus 1 times d. And so we have n of those, so we have n times 2a plus n minus 1 times d. But the problem is that we've actually counted this twice because we've set it out in one order and then we've done it in the reverse order below. We've counted it twice. So in order to account for that, we have to divide it by 2. And so that entire sum is going to be that equation because now we've divided that by 2. So let's use that equation to calculate the sum of the first 5 terms of the arithmetic sequence now, instead of just laying out all the numbers. So we go ahead and we substitute n equals 5. We substitute in as well that a equals 3, so it's 5 times 2 times 3, plus n minus 1, well n is 5, so 5 minus 1 times that difference of 7. So working from inside to outside in the brackets, and then using Bedmes, we get an answer for the sum of the first 5 terms of 85, just as we did the other way. So now let's move on to look at the second part of this question that said the sum of the series from 1/2 minus 3 plus 18 minus something all the way to minus 3,888. The thing to notice here is that we're multiplying each term by -6. And so if we're multiplying each term by -6, that actually means it's a geometric series. And so because it's a geometric series, what we're going to do is we're going to use a formula that we have for that. It's not quite as obvious to derive as the last one. So I'm just going to show that to you because this is a very well accepted formula that is used whenever we calculate the sum of geometric series. So it's n plus 1. So what that means is it's the term past the last term. So if the last term is negative 3,888, that means that Tn plus 1 is that times negative 6, which gives me in this case a value of 23,328. So the Tn plus 1 is that. We subtract the starting term of a half, and we divide that by r minus 1. Now r is negative 6, subtract 1, and you'll notice that this is Sn. We don't know how many terms are in the series, but we do know what the sum is despite that. So we go ahead and we simplify the numerator, we simplify the denominator, we divide those two things, and what we get is a final answer of negative 3,332.5. Now the interesting thing here, as I already said, we have no idea how many terms are in there, but the other interesting thing is that sum is actually smaller than the last term. And the reason for that is because the sign is switching on every term. So the sum is smaller than the biggest term in the series. Expanding and simplifying binomials is really tricky for a lot of people, but I'm here to show you just how simple that can be. We're going to look at 2x minus 3 to the power of 5 and how to expand that using Pascal's triangle. Pascal's triangle is all about the number of ways you have to go down on diagonals from a top point. There's one way to get to the second row, but if you go to this next row, you can go from the left or from the right, and so there's two ways to get there to the middle. If you go to the row below that, there's one way to get to the far left, but then if you look at this next point, there's one way to the left and two to the right, and so those add together to give you 3. And if you continue that pattern on and on and on, what you get are the following rows. Now the interesting thing here is that these actually correspond to the coefficients of whatever you're trying to expand as a binomial. So what we're going to do here is we're going to look at this. If you have an exponent of 1, then your coefficients will be 1 and 1. If you have exponent of 2, your coefficients are 1, 2, and 1, all the way down to 5. And our coefficients are going to be 1, 5, 10, and then 10, 5, 1. But we're only going to look at the first 3 terms. And this pattern that we see is going to continue for the other 3 terms that follow. So we go ahead and we write the coefficients 1, 5, 10. And we are going to add these all together because they're all distinct terms in this binomial expansion. Now we look at the first term in the binomial. It's 2x. We're going to start by raising that to the power that's on the binomial. It's 5. And then every subsequent term is going to be 1 degree less. So to the power of 4, then to the power of 3. And by the time you're at your last term, it'll be to the power of 0. Now the other term in the binomial, the negative 3 here, we're going to start that in the opposite direction. So we're going to start that at a power of 0 and count up. 2x counted down, the negative 3 counts up from 0. And so we then go ahead and we now have our 3 terms that we can expand and simplify. So 2x to the power of 5 is 32x to the 5th, and negative 3, anything to the power of 0, is 1. And then we are going to expand out the 2x to the 4th, and that's going to give me 16x to the 4. And then the 2x cubed gives me 8x cubed. And then the negative 3 squared is 9. So if we continue going now, 32x to the 5 times 1 is just 32x to the 5. And now what we'll notice is the sign changes here because we have 1 negative. So this gives me minus, and you multiply 5 times 16 times 3, you get 240x to the 4th. And then the next term has all positives, so it's positive or plus 720x cubed, and the next term would be minus again. The sign of the coefficient ends up changing every single time. Now remember, the coefficients we put in originally were 1, 5, and 10. But when we actually apply the parts of the binomial, that can determine if we have a positive or we have negatives as we go along. So it doesn't end up being 1, 5, and 10 at the end, but that factors into giving us those final numbers once we've simplified everything out. Unit 8 is all about financial applications, specifically compound interest and annuities. We're going to look at a compound interest situation like the equation shown at the top, followed by a future value situation, the one in the middle, and then at the end look at a present value situation where we have to rearrange that equation to solve for the variable n. This question says Marissa has just won a contest. She must decide between 2 prize options: collect a lump sum payment of $50,000, all one time, or receive $1,500 at the end of each quarter for 10 years. If she invests all her winnings in an investment that earns 6% per annum compounded quarterly, which is the better option after 10 years and by how much? So we're going to look at the first situation first, the lump sum of $50,000. And so she gets a present value of $50,000. And then she's going to invest that for 10 years quarterly. That means 4 times per year. We always take the number of times per year, and then we multiply that by the number of years. So 4 times 10, so the number of compounding periods is going to be 40. So she's going to get interest paid out 40 times on this $50,000 investment. The interest rate is 6% per annum compounded quarterly. So we write that as a decimal and divide it by 4. And what we do is we then make sure we divide the I by the same value that we multiply the N by, the number of years by. So we get I is 0.015, and we're trying to find the future amount. In 10 years' time, how much is it going to be worth? And the equation we use is that the future amount, A, is equal to the principal, P, times 1 plus I to the N. So P is $50,000, and then we sub the other numbers in. We get 1 plus 0.015 to the power of 40. And so effectively what we're going to do is we're going to multiply 50,000 times 1.015 40 times. That's what the power of 40 is doing. So that interest is accumulating 40 times throughout the investment. It's important to remember that we apply the exponent before we multiply it by 50,000. And so I've done that here. You don't have to show this step, but I've done that here just to show you how that works. And you should get a total number of $90,700.92. You've made $40,700.92 interest. That's quite significant over a period of 10 years. You've almost doubled your money. You started at $50,000 and you have over $40,000 now. Now let's look at the second situation. What if Marissa had received $1,500 at the end of each quarter? Those are regular payments that are made out to her, and she's going to put those into the investment as regular payments into the investment. The N value, the number of compounding periods, is 4 times 10, just like it was before, so 40. And the I value, same as before, again, whatever you multiply the number of years by, you have to divide the I by. And so we get 0.015 for that. And we're trying to figure out what that future value is. You could call that an A again, but I call that FV for future value just to distinguish it between a one-time investment like we had on the left. So the equation we're going to use is the equation right there. Future value is the regular payment times 1 plus I to the N minus 1 all over I. So we go ahead and we sub those numbers in, $1,500 for the R value, and then 1 plus 0.015 to the power of 40. Then we have to subtract 1 before we multiply into that by 1,500. And then we divide that by 0.015. And so the future value is equal to, just taking the steps with this, we do what's in the square brackets first, and we should get a value of 0.8140, and then that goes on from there. And we then divide all that by 0.015. And so that gives me that the future value should be a value of $81,401.84. Now that's significantly less than we would have gotten with the initial situation, but let's have a look at what the differences are. The first difference is how much did she actually put in, or how much was she paid that she put into her account? Well, her regular payments were $1,500 and she was paid those 40 times. So she actually received $60,000 in this second case. You'd think that would amount to more, but she only gets $21,401.84. So the difference between $60,000 and $81,000, about $21,000, that's all the interest she's earned. Well, the reason for that is because she actually has gotten very little interest on those later payments, and the initial payments early on were very low. They were only $1,500 and then $3,000 total and then $4,500. And so that money that was paid earlier on didn't get much interest because there wasn't a lot of money initially in her account. So the first option is better. And what she's going to get is she's going to get quite a significant amount more by using that first option. She's going to get $90,700.92, subtract the $81,401.84. So she's going to end up with just about $9,300 more interest by choosing option 1. The power of compound interest with a big upfront payment is super powerful for you. But regardless, she's still getting a lot of interest by using the other option. But if she had the money up front, it would have been a better option. So Marissa should have chosen the lump sum payment of $50,000. If you have student debt, do you ever wonder how long it's going to take to pay it off and how much you're going to end up paying total? Here's a perfect example that shows you the average in Canada, what that would look like. It says this: Kyla must repay student loans that total $28,000. She can afford to make $340 monthly payments on her loan. The bank is charging an interest rate of 7.2% per annum compounded monthly. How long will it take her to pay off the student debt, and how much interest will she have paid? So let's get down to it. The equation that we need to use here is the present value equation, but the value that we want to start with is that present value. So we're starting with $28,000 and we're paying that off down to 0. So that's why we're not using the future value equation. The regular payments that Kyla is making is $340. And the interest rate, the I value that we use is we make that a decimal, we take that then and we divide it by the number of compounding periods per year. And because it's compounded monthly, there's 12 per year, so we divide it by 12. And so we're trying to figure out how long it's going to take to pay off. We're trying to find the end value, and it's worth noting as well that the end value corresponds with the compounding periods per year. So that's 12 payments per year, and then there's however many years it takes to pay off. So the n is the number of months that we have to divide by 12 at the end. So the equation we're going to use is this. PV equals R times 1 minus 1 plus I to the negative n all over I. And it's just good to have an idea of what this actually looks like in reality. We have some amount that we're starting off with, and then over time we're going to pay it off faster and faster because more of our payments go towards the principal and less towards the interest over time. It's going to look a shape something like that. So let's go ahead and rearrange this equation before putting the numbers in, just because it's a messy equation and just the variables make it a little shorter to rearrange. So we're going to multiply both sides by 1 over r. And that's going to give me I times PV over R equals 1 minus 1 plus I to the negative n, what was in the square brackets. We can get rid of the square brackets now because that's by itself on the right. If we subtract 1 from both sides, now we get I PV over R minus 1. And that's equal to negative 1 plus I to the negative n. We're getting closer to rearranging for negative n here. But before we do that, we have to multiply by negative 1 to make that positive. And then whatever you do to one side, you have to do to the other. And so we're going to multiply the negative 1 in, which is effectively going to make the 1 positive and the IPV over R negative. So we could write that in the opposite order as 1 minus IPV over R. And then we have 1 plus I to the negative n. Now, in order to solve this, the only way to do this is using some type of logarithm. And so we're just going to use a basic logarithm. And if we take the log of the left side, we have to do the same thing to the other side. And what that logarithm does, without knowing more about logarithms, is it effectively just brings the exponent out front. And so we can write the same thing on the left as I had on the line previously, but now on the right, this becomes negative n times log of 1 plus I. And that exponent now is gone from that. So now what I want to do is I want to divide by the log of 1 plus I to get just negative n on the right side. Whatever you do to the one side, you have to do the other. And the logs don't actually cancel on the left side. And it's because it's very much like sine or cosine that operates on something. It's not like they're being multiplied and you can divide them out. So they operate on what follows. So it's very important you keep the log in both the numerator and denominator. The final step here is recognizing that there is a negative n left on the right. So we're going to multiply both sides by negative 1. And so we have the same thing we had above, but there's a negative on the left side, and on the right, the n is positive. And it's important to keep in mind that n is the number of months. We're going to get a large number. It doesn't mean it's going to take this many years to pay it off. It's the number of months. So let's go ahead and sub some numbers in and actually solve this now. So n is equal to negative log of 1 minus, the I value was 0.006. We're going to multiply that by the present value of $28,000. And we're dividing that by the regular payment of $340 that she's making. Then we're going to divide all of that by log of 1 plus I, 1 plus 0.006. So now we can go ahead and calculate what's after the logs. It's good to simplify that first just so we don't make mistakes. So if you do that, 1 minus the 0.006 times 28,000 over 340, you end up with approximately 0.50588. And then on the bottom, we can simplify that to 1.006. And if you then take the negative log of the numerator and divide by log of the denominator, we end up with almost 114, 113.916. And so you always have to get to that next payment to finish paying off the debt. And so we're going to say it's 114 months in order for her to pay this off. Now, I said that was the number of months. So if we divide that by 12, we end up getting 9 and 6/12, which gives me 9 years, 6 months. That's how long it's going to take her to pay off her debt. Now, $28,000, almost 10 years to pay it off, that's quite a significant time of someone's life. Well, how much interest did they pay? How much interest did Kyla pay here? Well, she paid $340 114 times. The last time might be a little bit less than $340 because we didn't quite get exactly 114, but it's around this number. So she pays $38,760 back, and she only borrowed $28,000. So that means she almost had $11,000 nearly in interest that she had to pay. So have a look back at the graph on the top right again, and you'll see that near the end the line is steeper, but towards the beginning of the time the line was less steep. And that's because at the end you're paying off more principal, you're paying it down faster, whereas at the beginning you're paying almost all of your payments towards interest. So it's really in your best interest, pun intended, to pay it off as fast as possible so this doesn't last longer and charge you more and more interest. In fact, 7.2% is not that big of an interest rate on a loan. Some people have credit card debt that could be 19 all the way up to 29%, and that interest rate could just swamp them if they don't get that paid very quickly. So it's very important you pay your debts down fast, but then you use this to your advantage by investing money over the long term to get interest working for you so that you can gain long term. If this has been helpful, please like and subscribe and consider sharing it with some friends. The video on the left is all about how to prove trig identities and more examples of that, which is the most difficult thing for many students in this course. So check that out. The playlist on the right has an entire list of all the lessons that I've made for this entire course if you want more breakdown for any lesson. Thanks so much for watching.